Good morning, dear student. In today's lecture, we are very much interested in the important point of our chapter, that is magnetic material, that is domain theory for ferromagnetic material. So, what is this domain and what are the postulates of this domain theory, and what is the relationship between magnetic susceptibility and the temperature? So these all points we discuss in this lecture. So if you consider the diagram, that is there the two diagram is there, in which the first diagram, uh, it is the ferromagnetic material. So the first diagram represents the ferromagnetic material in absence of magnetic field, and the second, that is ferromagnetic material in presence of magnetic field. So what is the domain, and what is the domain theory, or what are the postulates of this domain theory, we will discuss in this lecture. So before discussing, you should keep in mind that the diamagnetic materials and paramagnetic materials cannot be used to produce permanent magnet. So diamagnetic materials and paramagnetic materials cannot used to produce permanent magnet. So substances which is used to prepare the permanent magnets are ferromagnetic materials. So you should keep in mind, the important point is that, so ferromagnetic material is used for synthesis of permanent magnet. So let us discuss the domain theory of ferromagnetic material. So if you consider the first postulates of this domain theory, according to this uh, postulates, the first postulates is your ferromagnetic domain. So the first characteristics or first postulates is your ferromagnetic domain. Ferromagnetic domain. Ferromagnetic domains. So initially you should must understand that the diamagnetic and paramagnetic material cannot be used to produce permanent magnet because it does not shows permanent magnetism, and therefore the ferromagnetic materials are used for the synthesis of permanent magnet. And the first postulate, it is the ferromagnetic domain. So what is this domain? If you consider the atoms of ferromagnetic materials, so we know that every materials consist of atoms. So the atoms of ferromagnetic materials are grouped together in a small region called domain. So if you consider this the diagram, and this is the one domain, that is, if you consider these whatever the materials of this ferromagnetic material is shown, this is nothing but your atomic magnet. So they are nothing but your atomic magnet. So what is this domain? The atoms of ferromagnetic materials are grouped together in small region is called domain. So if you consider this is a one domain, in which, if you consider for our convenience, we consider the four atoms are grouped together. So this is one atom, this is second, third, and fourth. So atoms behave as a magnet, and therefore they are considered as the atomic magnets. No doubt the atomic magnetism or the magnetic moment in atom is due to the motion of electron, that is spin motion and orbital motion of electrons. And due to this, here we not considering the electrons because atom itself act as a magnet, and therefore they are considered as atomic magnet. And these are the group of atoms. So this is one group, this is second group, this is third, fourth, fifth, sixth. So in material there is a lot of groups. So groups of groups, that is, the atoms of ferromagnetic materials are groups together in a small region is called domains. So this is the group of atoms, and this part is considered as a domain. So there is a different domains. there is a different domains, and each domain, if you see, the direction of each atomic magnet is different in each domain, because if you consider this domain, every atom in this domain have, we can consider a special type of interaction, and therefore every domain have a different direction. So at least you should understand that what is this domain. The atoms of ferromagnetic materials, so whatever the atoms present in ferromagnetic materials are grouped together in a small region is called domains. So group of atoms, okay, or the atoms in ferromagnetic materials are groups together in a small region is called domain. So this is one domain, this is second, third, fourth, like this. So the domain is nothing but the group of atoms in a small region, okay, and this atom is considered as a magnet. Therefore we can consider it is an atomic magnet, because atom is also behave as a magnet. It will shows net magnetic moment, and therefore we consider atomic magnet. So group of atoms in a small region, so they are group together in small region is called domain. A domain is a region in which all the atoms are arranged in such a way that their magnetic moments are parallel to each other. So this is the important point, no doubt. It is the group of atoms, okay. The group of atoms is nothing but your domain, but in domain the metal at but in domain the metals are arranged in such a way that the magnetic moments are parallel to each other. So whatever, if you consider the direction of this magnet is the same, is same in this domain, because if you consider the magnetic moments are parallel to each other, the magnetic moments are parallel to each other. So this is the important point. So let us discuss these postulates. So you should understand the difference, that is, in absence of magnetic field, the domain having a random motion, and if you consider in presence of magnetic field, they having only one direction, that is, all these atoms in domain have same direction, having a same magnitude, but in absence of magnetic field they have a different magnitude. So the first important point is that the first postulates, that is ferromagnetic domain, it is the first postulates in which the first point is what, the atoms of ferromagnetic materials. So atoms of ferromagnetic material, atoms of ferromagnetic material, atoms of ferromagnetic materials are together grouped together in small region called domain, called domain. The second important point is that in domain all the atoms are arranged in such a way that, so the arrangement of all atoms in domain, arrangement in domain in such a way that the magnetic moments, the magnetic moments the magnetic moments are parallel to each other, are parallel to each other. So this is also the important point. So if you consider every domain, the magnetic moments are parallel to each other. So this domain, if you consider all these atoms having uh, same magnetic moment, because all they are parallel to each other, so magnetic moments are parallel to each other. So the direction of each atomic magnet is same, the direction is same, that is at right hand side. So for this domain it is upward, for this domain it is downward. So whatever the direction of this atomic magnet, it is same, and therefore the magnetic moments are parallel to each other. So the third point, it is that within each domain a special type of interaction called exchange coupling is exist. So special type of interaction special type of interaction is exist. So within each domain a special type of interaction is exist called a special type of interaction is exist called exchange coupling. So in every domain there is a special type of interaction is called exchange coupling is exist between the adjacent atoms. Exchange coupling exist among the adjacent atom, and therefore all all the dipole moments all the dipole moments of all atom within the domain in the same direction. Because so why the magnetic moments are parallel to each other? The second point is very important, that is the arrangement of atoms in each domain in such a way that the magnetic moments are parallel to each other. And why the magnetic moments are parallel to each other? Because in each domain and there is a special type of interaction is exist among the adjacent atom. So special type of interaction is exist between the adjacent atom, and this interaction is called exchange coupling interaction. This interaction is called as exchange coupling interaction, and due to this interaction the dipole moment or the magnetic moments of all the atoms within the domain is in same direction. Within the domain in is same direction. The next important point is that the next important point is that in absence of magnetic field, so this is the figure in absence of magnetic field. So ferromagnetic material in absence of magnetic field, so no magnetic field is applied. So in absence of magnetic field, different magnetic moments pointing in different direction. So if we see this ferromagnetic material, different magnetic moments having different directions. So this magnetic domain having a right hand side direction, this is upward, this is downward, okay, like this. So in absence of magnetic field, so we can consider in absence of magnetic field, in absence of magnetic field, different magnetic moment different magnetic moment different magnetic moment in different magnetic moment pointing in different direction, pointing in a different direction. So every domain having a different direction. So in absence of magnetic field, this ferromagnetic material, that is in absence of magnetic field, different magnetic moment pointing in different direction. So every domain having a different direction, so they are pointing in different direction, and therefore, so what happened due to this? And therefore the net magnetic moment or the total magnetic moment of this domain, so due to this different magnetic moment pointing in different direction, the total magnetic moment of this domain will cancel will cancel will cancel will cancel with each other, will cancel each other. So whatever the magnetic moment of right hand side, it is cancelled due to the magnetic moment of left hand side, or whatever the magnetic moment due to the upward direction is cancelled by the magnetic magnetic moment due to the downward direction. And this is the reason, that is in absence of magnetic field, different magnetic moments pointing in different direction, and therefore the total magnetic uh, moment of this domain will cancel, or total magnetic dipole is of this domain will cancel each other, and the material will remain unmagnetized, and which results, and the material remains unmagnetized, material remains unmagnetized, no doubt. So every domain having magnetic moments are parallel to each other, but the net magnetic moment is zero, and therefore the materials remains unmagnetized. But in presence of magnetic field, but in presence of external magnetic field, all these domains are aligned themselves in such a way that the direction of the magnetic field along the direction of magnetic field, that is, the next point is very important. In presence of magnetic field, in presence of magnetic field, in presence of magnetic field, so this is the diagram. So it is in presence of magnetic field, in presence of magnetic field, in presence of magnetic field. So in presence of magnetic field, all these domain, the domain align along the direction, align along the direction, align along the direction of external magnetic field, external magnetic field. So in presence of magnetic field, the domain align along the direction of external magnetic field, means whatever the direction of applied magnetic field. So this, if you consider, this is the direction of applied magnetic field H, or H0, we can represent the strength of applied magnetic field, then the same direction of this domain, so they are aligned themselves along the direction of magnetic field, and they shows magnetization, and they shows magnetism, and they shows magnetism. So this is the uh, domain theory of this ferromagnetic material. So you should remember why the ferromagnetic materials are used in preparation of a permanent magnet. Second, the first postulates that uh, the atoms in ferromagnetic materials are grouped together in a small region is called domain. Every domain have a parallel magnetic moment, but if you consider, in each domain, the dipole moment, that is, the direction of each magnetic moment pointing in different direction, that is, whatever the magnetic moment in each domain having different direction, whatever the magnetic moment in each domain having different direction, and due to this, the net magnetic moment is zero, and the net magnetic moments of this domain is cancel out with each other, and the material is unmagnetized. But in presence of magnetic field, the domain align along the direction of external magnetic field and shows magnetism. And the second postulate is that the internal molecular field or exchange coupling reactions. So the second postulate is that the first postulate is your ferromagnetic domain, and the second is your special type of interaction within the ferromagnetic atoms, that is, we can consider it is the second postulates. Second postulates, it is your exchange coupling interaction, exchange coupling interaction, exchange coupling interaction. So we know that we already discussed that within each domain a special type of interaction called exchange coupling is exist among the adjacent atom, and therefore the dipole moment of all atoms within the domain is the same direction. So this is the reason behind that every domain having same direction, not every domain, that is, whatever the atoms or the magnet having whatever the atoms and whatever the magnetic moments are parallel to each other. Okay, whatever the atoms, or we consider a domain, then the magnetic moments are parallel to each other, because this is due to the exchange coupling interactions. So if you consider one of the domain, they are all parallel magnetic moment, and this is due to the exchange coupling interaction. So spontaneous magnetization in each domain Spontaneous magnetization in each domain in absence of external magnetic field is due to the presence of internal molecular field called exchange field, or it is known as exchange coupling interaction. So spontaneous magnetization, no doubt, this ferromagnetic material in absence of magnetic field shows magnetization, and the reason behind that is, in absence of external magnetic field, this material shows magnetization is due to the presence of internal molecular field, or called internal molecular field, called exchange field or waste field, or the exchange interaction. So the important point is that is, the spontaneous magnetization spontaneous magnetization in absence of in absence of external magnetic field. So we already discussed in previous lecture, that is, when we studied the ferromagnetic material. So spontaneous magnetization in absence of external magnetic field is due to is due to is due to the exchange coupling interaction is due to the exchange coupling interaction is due to the exchange coupling interaction. It is also known as it is also known as exchange field exchange field or Weiss field, because Weiss is a scientist who derived the theory for the domain theory of ferromagnetic material, is known as exchange field or Weiss field. The internal molecular field tends to arrange the atom in such a way that the magnetic dipole moments are parallel to each other, producing the strong spontaneous magnetization in each domain. So these interaction, that is exchange coupling interactions, tends uh, these interactions tends to arrange the atom in such a way that the magnetic dipole moments are parallel to each other, producing the strong spontaneous magnetization in each domain. So this is all about the domain theory of ferromagnetic material. In the next lecture, we discuss the relationship between magnetic susceptibility and temperatures. Many times this question is asked in theoretical question paper when the pattern is theoretical. So the relationship between, how will you derive the relationship between magnetic susceptibility and temperature? So it is uh, in next lecture we will discuss the relationship between magnetic susceptibility and temperature. Thank you.